Ladies and gentlemen, I would like to welcome you to our presentation at the ACI Fall Convention in Dallas. Our title of our presentation is ATENA Software, Latest Development for Digital Twin and 3D Concrete Printing. For those of you who are not familiar with our company, so let me first give a few introductory words about what we do. We develop technology and software for nonlinear simulation or advanced modeling and simulation of concrete and reinforced concrete structures, as it is summarized by the example applications on this slide. And on top, you can see our motto, which is test your structure before you build it. Nowadays, we have also the expanding 3D printing industry, also for concrete. So we are expanding this motto to test your structure before you print it. And I will come to that later on in my presentation, where I will show some advances in our technology for the application of 3D printing of concrete. So why nonlinear simulation of structures is useful in practice? As we can see, we have various advanced structures that we can, where it is advantageous to make more advanced modeling and simulation. It's one of, let's say, the deepest advantage or that we can obtain from nonlinear analysis is that it can provide a deeper understanding of the structural behavior for design as well as in maintenance of existing structures. Well, this slide should emphasize that, of course, the expert judgment and basic engineering knowledge is still essential, and nonlinear analysis should not be understood as a method or tool to replace that. However, we have to understand that most of the formulas which we use in design are quite empirical and are based on laboratory experiments. Typically, we use the experiments of beams, slabs, some bigger slabs or small plates or walls. And based on that, we develop formulas which are often empirical, and we try to use them to design quite complex situations nowadays, like various steel pieces embedded into concrete, or some very fancy architectural shapes. And or nowadays we have the technology of 3D printing, where of course the standard methods are very difficult to apply. So this is where nonlinear analysis is an excellent tool to supplement and enhance our classical methods. Well, a little bit about the background of the technology that we are using. Our software is based on finite element method. That means our structure is divided into small pieces, typically rectangular or brick shape or triangular. And inside, we have some mathematical model of this finite element method. And inside this finite element, we typically evaluate the strains and stresses and integration points. So inside these integration points, traditionally we use linear material models, but we can use also nonlinear models, taking into account cracking, crushing, or reinforcement yielding. How such an analysis proceeds is shown on this graph at the bottom left. So in such an analysis, we typically have to load by steps. And in each step, we always have two stages, kind of a predictor where we assume elastic behavior, and a corrector, which brings us result back to the true or more realistic response. So this is also shown in these mathematical formulas here in the middle. And all this development is going back quite a long time ago to the work of NGO and Skordelis, Rashid, Chervenka, and so on. For the nonlinear behavior, currently we are using the crack band theory, which was first proposed by Bajant and al. In 1983. So very brief summary of the material models. So the material model in our ATENA software is a fracture plastic model. By that I mean we are using a Rankine fracture mechanics based model to simulate concrete cracking. And in the compression, the compressive behavior and compressive crashing is controlled by a plasticity-based model, which consists of hardening and softening. Like in tension, also in compression, we take into account the energy dissipation by using an analogical model to the crack band model. Now we can call it crash band model. And with this, we can take into account also the size effect, the fact that large structures tend to be more brittle than small structures. Well, this is very essential is to validate these models. And the best method for validation is the participation is in various blind predictions. I'm showing few blind competitions where we participated, and usually we were quite successful in our methods and models being always providing quite accurate and results with good predictive accuracy. Maybe I mention now some of these blind competitions, more recent one. So one from 2015, famous Toronto beam, very large beam. I am not going to spend too much details on this because I think it is quite famous. Let me just briefly show some simulation results of a nonlinear simulation and how it can predict well the cracking pattern and also the load carrying capacity. So the experimental was 685 kilonewtons. ATENA predicted 745, so about 7% above the experimental one, but very good prediction of the crack pattern. Here I showed the two results. There were actually two experiments, one unreinforced, that's what I showed you before, and one with reinforcement. So these circles indicate our results. So you can see in both cases, we were in this yellow area of 10% accuracy. So we were announced as winners for this competition, but let me go back to, or let me continue with another competition, which is more recent one from 2021. This time, very similar beam tested at University of California at Berkeley. Here you see the results. Again, it was a single beam, but one side was without reinforcement, without shear reinforcement, which was later strengthened by these ties, and then the beam was reloaded to crack it on the other side. So that's why we have these two results. Here you see with the green line indicates the measured, what was obtained in the experiment. And the yellow circle indicates our results. So this time we slightly underpredicted. And this is actually shown here. We underpredicted by 25%, which I'm sorry, this we underpredicted here. It looks more like 50%, yes, but we have to take into account that there is also an important contribution to the shear force from the self-weight, which was not reported in the evaluation of the experiments by the organizers. But if we correctly evaluate the error we obtained, we should really take into account also the effect of the self-weight. So if we do that, we see that our error in this analysis was a little bit worse. We underpredicted by 25% for the first test and 22% for the second test. So this is always a good to learn. So let me summarize. This is a good opportunity to learn also. So let me show the results. This is the Toronto test 2015, where we had a very good prediction and we were the winners. And these are our results from the Berkeley experiment 2021, where our results were not so good. And one of the reasons afterwards we evaluated and learned from this was that we wanted to really be on the conservative side in our predictions. So we took into account quite significantly the shrinkage effect, and this very much reduced our predictive prediction of the load carrying capacity. So this is also something we learned from this, that in these experiments, the shrinkage was not that, the contribution from the shrinkage to the cracking was not so significant. Another important thing is that there is a important parameter when we make these nonlinear analysis, and that is the shear stiffness of the cracked concrete, which of course is not a parameter we know, so we always have to estimate it. And the estimation of this is very important. And if you make a incorrect estimation, you may, like in this case, underpredict the real strength. Another example or another blind prediction, also very nice one, also from Berkeley. That was these columns. This time it was a column with cyclic loading. An important result that we were required to predict was the ductility. So this is this bottom. This shows the scatter of results from all participants. Our prediction was here, so we were really very much on target with the ductility capacity. Also, our quite good prediction for the strength capacity somehow underpredicted the initial stiffness, or over-predicted actually the initial stiffness. Let me just show some results from the cyclic, some animation of some results so that we can get a little bit relax ourselves from all these equations. So here you see the simulation, you see the crack opening and closing always. And very important in this column was the development of a shear crack in the middle section, because the middle section, as you could have seen on the previous slide, was with lower shear reinforcement than the end section. So that's why the final failure mode was mainly governed or controlled by the development of the shear crack in the middle section. So overall, these predictions, or these blind predictions, I think show that our technology is quite reliable and can predict have a real predictive capabilities for the structural behavior. So now I would like to spend the second part of my presentation of showing some, or inform you about the latest development in ATENA software. So one of the major development lines is that we develop a totally new user environment for our software. We call it ATENA 2023, as we expect to release the final version, commercial version, at the beginning of next year. Here you can see some first overview or first glimpses of the user environment, where what I want to emphasize, it will be based on a BIM model, so it will have a native BIM model behind the software. And another interesting possibility there will be the full support of Python scripting to help users in their modeling and modeling work. And then, of course, before this version is released, we are also right now releasing a new version of ATENA, which is a, let's say, incremental improvements. The number is 5.9.1. And more information about this version you can find on our website. And now we are, because of the modern trends in using nonlinear analysis, I would like to also emphasize a little bit and show some examples of ATENA application for digital twins and for 3D printing. So let me also briefly summarize the new new features in this new version 5.9.1, which we are releasing right now. This is really an incremental update. And if I want to emphasize some of the new things, a very interesting one is a new licensing options, which allows very easy trial version. So you can download the software and almost immediately can evaluate it for 30 days. Then in the program itself, we have new creep models for the ACI, for the Canadian code. We have some bond models improved and modified to simulate aging and deterioration based on time, temperature, or corrosion. And then there are various minor improvements in the post-processing, and in the pre-processing, we are using a new preprocessor version, Git version 16. Interesting there is that it supports new import formats like the IFC4, that means Building Information Model format. And for 3D printing simulation, good and interesting feature is the support for G-code, which simplifies the model execution and preparation for the simulation of 3D printing. So let me go now to the digital twin concept, where we are using ATENA more and more often nowadays. And I would like to show two examples. One is an example in Czech Republic. It is a pre-stress concrete bridge, box girder bridge. And the second one is a bridge in Germany, which is a reinforced concrete bridge. And so what is this digital twin concept? This digital twin means that there is a close connection and calibration of the numerical model of the virtual model by a close cooperation with the monitoring. So in these examples, we were using a monitoring system which allows to evaluate the real loads on the bridge. Of course, some calibration there is required by predefined trucks with a predefined weight, but there is a rangefinder which can find the speed of the cars and the number of axles the vehicles have. And of course, some strain gauges needs to be installed. It is a very easy to install system. It can be installed in, let's say, 2 hours. And it can provide very interesting results. This is, for instance, what typically results you obtain when a single vehicle is passing. So you have results from the strain gauges. In addition, you have these readings, this green line indicating the readings from the range sensor, from the laser scanner, which allows to determine the speed of the vehicle as well as the number of axles of the vehicle. And so we can obtain these kind of results, like for instance in time we can see the probability of various vehicles with a certain weight, or we can also evaluate the speed or typical speed of the vehicles throughout the day. And we for each vehicle we obtain this kind of information, which shows the weight of the vehicle, the number of axles, the length of the vehicle, speed of the vehicle, and so on. And this is then used to perform the calibration of the numerical model. And with the numerical model, what we typically then perform a durability analysis also. So we calibrate the model based on these experimental data in close cooperation with the monitoring, but then we use it for the life or long-term predictions. For that, we also need to take into account the durability. That means, for instance, corrosion and creep and shrinkage and so on. So for the durability model, we have a model where we combine it with, where we combine the mechanical model with a chemomechanical model, which considers first the diffusion of chlorides and then reinforcement corrosion. This model, main features of the models consider basically the increase of corrosion depending on these typical situations. First, when the chlorides concentration, critical chloride concentration is reached at the reinforcement depth, and then when that's when corrosion starts. And when cracking of the cover and spalling of the cover, these points indicate a change of the corrosion rate. So all this can be taken into account by schematically it is shown on this graph. So if you think about some structure with the reinforcement model inside, this is what we have in our ATENA model. There is a discrete level, a discrete model also of reinforcement. So for each reinforcement, we know the distance of the reinforcement from the surface, which is subjected to some chlorides propagation or carbonation. And we can then use just a 2D, one-dimensional model to simulate the chloride propagation, also taking into account the possible presence of cracks. As you can see here, at the location of the crack, we have a much higher corrosion rate, as is indicated by these red zones. So with this model, we can have quite accurate predictions of the long-term behavior or long-term reliability. So let me show some results for the first bridge, which was this pre-stressed reinforced concrete bridge. This shows kind of a transparent, the top figure shows the transparent view of the bridge with the pre-stressing tendons inside and also the crack development at the point of collapse during the simulation. Here you also see this typical overloading curve, kind of a pushover curve if you think about it, and then the development of a shear failure close to the support. So what happens is that we can perform such an overloading, which was demonstrated before, kind of a pushover analysis, for different times. So we consider the chloride propagation, corrosion development, and then we can obtain such a pushover curve at different times. And from this, we can calculate the load carrying capacity of the bridge as it evolves in time. So of course, we need to consider some probabilities. In this analysis, we use the model from the FIB model code, where we performed one analysis with mean properties, one analysis with characteristic properties, and based on that calculated the design load. And from this, you can see that the strength of the bridge is sufficient to survive for almost 100 years. Now, here I'm showing some slides from the other pilot example from Germany. So what we can see here on the top left figure, this shows the chloride concentration with the model I described very briefly previously. Chloride concentration at the depth of reinforcement, yes, in time. This is over 150 years. The bottom left shows the reinforcement corrosion, how it develops. So you indeed can see that the chloride concentration and corrosion develops at sooner at the points, at the locations where there are some cracks. Top right shows the reinforcement stresses and also the cracks in the transparent view. This is also one of the unique features of our software, that it can nicely visualize the cracks, not only on the surface, but you can also visualize the most important cracks inside, in the interior of your structure. And the bottom shows the crack width. So with this approach, with this approach, we can make similar analysis like before. So that means we consider the chloride propagation for certain time period. And at the end of the time period, we always subject the structure to some overloading by the design loads. And in this way, we can predict what is the load carrying capacity at the different times. And again, that's why you can see here on the graph on the left, those are the various load displacement curves, or you can think about them as pushover curves. The green one is the original bridge without any damage due to corrosion. And in time, gradually we see degradation. So for instance, blue is 50 years, 100 years, and if you go to 150 years, there is not enough load carrying capacity even to sustain the loads. The loads are displayed on the vertical axis and they are normalized with respect to the design load. And we can have the similar figure like before, that we plot the strength of the structure in time. And here we can see that again at about 100 years, there is not enough safety anymore. And the bridge would have to be maybe retrofitted or maybe taken out of service. If I look at the two bridges, you can nicely see the same normalized load carrying capacity curve in time. And it is interesting to observe that because of the different design, both bridges have a different sensitivity to the long-term effects. The reinforced concrete bridge is much more sensitive. There is a steeper degradation due to corrosion. That's because the pre-stressing tendons are hidden much deeper inside of the bridge walls. So it takes much longer time for the corrosion to start and to proceed and not cause significant damage. Okay, so last example or last technology or development on our software I want to show is the simulation of digital printing of concrete. For the demonstration, we are using the building Prvok, which was one of the first 3D printed buildings in Czech Republic. We are using very fresh concrete, so there is a danger of collapse. So that's why simulation is a very useful and necessary tool. Now we will go to open our preprocessor and use the G-code. So this is the context of the G-code file, which we can import into ATENA software. And currently the G-code for the Prvok house consists of 6 parts, so we have to import one part after another. You can see the import of the first block, then the import of the second block, and we can see that our model consists of 2 blocks at the bottom. There is one wall block on the left side, another wall block on the right side, and then there are 2 blocks at the top. This allows us very accurate and realistic modeling of the 3D printing process. So you can see the layers. The program can of course control how in detail are the layers modeled. So we can either model each layer, or in this case we are modeling these 2 layers are lumped into a single line of finite elements. We are using fracture plastic material, which is generated by the expert system with all material parameters being time dependent. Then these materials are assigned to the model, and we need to also provide supports at the bottom and connections between the individual blocks of the G-code. When it is finished, we can save the input data and we can upload it to our cloud server, where we can then perform the analysis. So we can start the running of the analysis, and when the analyses are completed, we can look at them. Either we can review the results in, let's say, graph form, which here nicely shows the collapse of the structure at this point. If need be, we can look into the cloud computer to review the results in more detail, as you can see now, and we can observe the collapse on the right wall and also the increase of displacement at about 1.4 meters. So I would like to summarize showing the results from for the Prvok simulation. You can see 2 simulations, one using the speed of 200 millimeters on the left, and on the right is the speed of 20 millimeters per second. As you can see, the one on the left collapses at about 1.4 meters, and the one on the right can be built all the way to the top, although we can see some large deformations.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.